Okay, good afternoon, everyone. Welcome to the Claris Pavilion. My name is Emma. I'm a PhD candidate at the Alfred Wegener Institute and the Ludwig Maximilian University of Munich. And I'll be introducing David Rounds and Christina Drager to talk about the future of glaciers and how it relies on today's policies. And so, give it away to David.
Thanks a lot, and thanks everyone for being here. This is really wonderful to see many faces in the audience today, as well as to those online. So it's greatly appreciated. Today I'm going to talk about some of the latest and greatest glacier projections, how it relates to the policies that we're talking about being present here, our emissions reductions, as well as how these impacts are actually experienced, right? We see both global impacts, we see regional impacts, and we see local impacts. And so we're going to talk about a variety of those here today. So first and foremost, we know that the glaciers are responding to climate change. They're one of the easiest things to look at and know what has happened over the last several hundred years. Here's a depiction of Rhone Glacier from 1850, and here's what it looks like in 2000, right? It has retreated, and it has actually sunk. Its surface has lowered substantially as well. Here's an example in Alaska of a tidewater glacier in the 1940s and here in the 2000s. Once again, you can see that it's essentially deflated, it's thinned, and it's retreated substantially up glacier as well. Here's the glacier that I did my PhD work on, Imja Glacier in Nepal. Here's an example of it in 1955. In 2007, you can see that once again, it's thinned, and now it has a very large proglacial lake at its terminus as well. And this is not just in these select locations, right? This is everywhere around the world, whether it be in Greenland, in the Antarctic, in Africa, in the US, in the Andes, in the Arctic, in Alaska, in the Everest region of Nepal. Anywhere that you look, the glaciers are melting, right? And why do we care? We care for multiple reasons, but a large part is because of the impact that it has on society and the subsequent hazards. So sea level rise is one that gets a lot of attention, and rightfully so. All the coastal communities are going to be affected by these glaciers. But we also have a lot of rock falls, slope instabilities. We have avalanches. We have uncertainty with respect to water resources and hydropower. It varies depending on how far upstream we are, how reliant the local communities are on that water. Glacial lakes that are expanding. And the thing that I really want to highlight is that the scale of these impacts really varies, right? We have some that are focused on a global level, some that are focused on a regional level, and others that are very much on a local scale. And we've seen these impacts today in our recent past, and we know that they're going to continue to be impactful in the future. The other thing that I'm not going to speak about too much today, but I do want to highlight, is that these impacts are disproportionately felt by marginalized communities. So climate adaptation and climate mitigation is an equity and justice issue. So what are we talking about today? First and foremost, we're going to talk about how these glaciers are responding to climate change. And so we want to understand, dependent on the emission scenario that is in our future or the temperature change level that's in our future, what will the glaciers look like and what will the associated hazards look like? And so as I mentioned before, glaciers are losing mass everywhere around the world. And so here's a great study that was done several years ago in 2021 that showed how much the surface of these glaciers is lowering. You can see in the reds, those red colors are showing you where the surface is lowering on average by about 1 meter per year. Some of the bluer colors or the whiter colors are showing some glaciers that are experiencing more or less very little loss, if not slightly positive. And that's really located in the Karakoram anomaly. So in that high mountain Asia region, which is now also started to see some loss in more recent years. Now, what we do as modelers, I'm a glacier modeler, what we do is we take all of that data and we incorporate it into our models to try to improve our ability to predict what's going to happen to these glaciers in the future. And so here's some of our latest projections that are done for different shared socioeconomic pathways. So we're looking at how are the glaciers going to respond? And we see that from 2015 to 2100, if we have a reduction in our greenhouse gas emissions for SSP 126, we see about 27% of our glaciers globally are going to be lost. When we look at our higher emission scenario, we're looking on the order of 40 to 45% of our glaciers being lost. Really a substantial difference that highlights how much of an impact we, being present at COP, can have on preserving our glaciers. The other thing that's very important to note is that these are about 10 to 15% more glacier mass loss than the projections that were used in the latest IPCC report, right? So this is new information that has come out since IPCC AR6 that shows that we actually have more mass loss, and thus the urgency that we need to act with is even higher. Now, I mentioned that we looked at these different SSP scenarios. In order to support the conversations that are going on here, we translated those into temperature change scenarios. So we looked at aggregating those scenarios based on their increase in global mean temperature at the end of this century relative to pre-industrial levels. And you can see the curves for different 1.5 degrees all the way up to 4 degrees. And the top curve is showing you what the percent mass remaining is from now until the end of the century. And on the right-hand side, what you can see is the relationship between the mass at 2100 relative to those different temperature change scenarios. We have a lot of scientists here. Pretty much anybody would fit a straight line through that, right? The ability of our actions to reduce the temperature will directly lead to the preservation of our glaciers. Every 1/10 of a degree matters. On the bottom here, what you're looking at is the number of glaciers that are going to be lost. And we project that even in the best case scenario, by number, we'll lose about 50% of our glaciers. For those higher temperature change scenarios of up to 4 degrees, we're looking at losing close to 80% of our glaciers globally. Once again, you can see more or less a linear relationship. Every increase in temperature matters. Now, most of the glaciers, the reason for that discrepancy between the mass that's remaining and the number of glaciers that are remaining is because most of the glaciers that are lost are small. So a lot of the 216,000 glaciers on our planet are actually less than 1 square kilometer. So these are really, really tiny glaciers, and most of those are going to be lost. That's unfortunately the reality, even in a 1.5 degree temperature change scenario. When we get to those larger glaciers, they're not going to be lost completely, but they're going to be substantially reduced in size as well. And so when we think about things like sea level rise, it's really depends on what's going to happen to those largest glaciers because they have the most mass to be able to contribute to sea level rise. But when we think about glaciers all over the world and at local levels, those local glaciers, those smaller glaciers can also be really important. And we'll touch upon that a little bit today here as well. Now, the other thing I want to highlight is I just showed you some global statistics, right? We also have the ability to look at how every single region varies in response to these temperature change scenarios. And so once again, this is looking at the mass at 2100 relative to 2015 and how it varies as a function of those temperature increase scenarios, that global mean temperature change. And so I want to highlight 2 things. First and foremost is that the mid-latitude regions, we see they are incredibly sensitive to 1.5 degrees to 3 degrees. You can essentially see this really leveling off beyond 3 degrees, and that's because the glaciers are almost all gone. So our actions can really preserve a lot of the glaciers in these regions. There's still going to be a lot that are lost, right? Even in the best case scenario in many of these regions, we're losing up to half of the glacier mass in these regions. But that's a big difference between 50% of the glacier mass lost and close to 90 or 100% of the glacier mass loss, right? I personally enjoy these glaciers, would love to see them stick around, right? In other regions, we see, especially these larger regions like Alaska and the peripheral glaciers in the Antarctic and the subantarctic, we see that there's going to be substantial mass that is lost, but it's more linear. And the reason being is because there's a lot more mass to these glaciers. So some small areas of this might see complete deglaciation, but there's going to be a lot of mass that remains, and that's why we see that linear trend in this mass. Now, one of the most exciting things that we got out of this research was we calibrated our model with data from every single glacier, all 216,000 glaciers globally. And so we can start to look at what is the impact on a very local level. And so here, once again, we're looking at the mass at 2100 relative to 2015. The blue colors are showing you where you have about 80% or more mass remaining by the end of the century. You don't see much blue, but you do see some. The red colors are showing where you only have 20% or less mass remaining by the end of the century. The other thing that we really called out here is the white circles that are outlined in black. That is an area where all of the glaciers are lost, complete deglaciation. And so we show this for different temperature change scenarios. So here's what you see for 1.5 degrees, 2 degrees, 3 degrees, and 4 degrees. I'm going to invite you to look at Central Europe, for example. At 1.5 degrees, we already see that there is some deglaciation that is happening. That's inevitable. If we go to 2 degrees, 3 degrees, 4 degrees, we see that we're losing almost all of the glaciers there, or there's very, very little pockets of glacier ice that is remaining. The same thing in Alaska, in southeastern Alaska. We have some moderate yellow colors indicating roughly 50% of the glacier mass remains, some areas of deglaciation as well. As we move through those higher temperature change scenarios, we see deglaciation and we see much darker red colors, meaning that there's very little mass left in those regions. Now, one of the things that we really care about and what we're really here for is because it's not just the high mountain communities that are affected. It's also all of the coastal nations as well. And so for that matter, we think about these temperature change scenarios and we put it into a framework as to what is the glacier's contribution to sea level rise from 2015 out to 2100 for these different temperature change scenarios. Once again, we see that glaciers will contribute about 90 millimeters, even in a best case scenario between this time period. If you look at these higher temperature change scenarios, at 2 degrees, we're looking at a contribution of 100 millimeters, and even higher for 4 degrees, we're getting up to 150 millimeters. Once again, this really shows that we're going to have an impact from the glaciers that's going to be inevitable. But 90 millimeters versus 100 or 150 shows how big of an impact that our actions here this week, over the last couple of weeks, can have on reducing the glacier's contribution to sea level rise, which is roughly about 20% of the contribution to the global mean sea level. More recently, just a couple of weeks ago, there was a study that came out that looked at multiple glacier evolution models. So the previous was only focused on this Python glacier evolution model, or PyGEM, on the right. And this study showed when we look at the projections, including 2 additional glacier evolution models, it pretty much confirms what we found in this study that was done in 2023. So the robustness of these results has been increased by these multi-model ensembles. Now, we're going to take a turn to start looking at some of the more regional and local impacts. But before we do, I just want to highlight the global impacts, right? Sea level rise affects pretty much everyone, all coastal communities globally. The other thing is these glaciers, their snow is white. They have high albedos compared to terrain, right? So there's a feedback associated with the albedo, with its absorption or lack thereof of the radiation. And that's why we see higher rates of temperature increase in the mountains compared to the global mean, right? This Arctic amplification pattern. The other thing that I'll note is we'll start talking about some of the more local impacts, but really these are indirect impacts, right? When we talk about water resources and their use in agriculture, that really has a global implication associated with it. When we talk about hydropower, renewable energy, right? We're talking about global markets. When we talk about tourism and culture, that is something that should be kept for our global society, right? So now I want to shift over and introduce Christina Dreger, a PhD candidate at the University of British Columbia, who's going to share a little bit about the regional impacts in Western Canada.
Yeah, thanks a lot, James, for the introduction. Yeah, so we've just heard that mountain glaciers are declining rapidly, and that this trend has even accelerated. This trend has even accelerated in the recent past. And so this has vast implications for global sea level rise, but also especially for communities at the local level, and especially also for the millions of people that live further downstream of the glaciers. So what I would like to talk about today are the local impacts that we see from glacier loss in Western Canada. So to do so, we first need to estimate how mountain glaciers are melting on a local level. And glaciers are complex, and various factors are influencing how they are melting, and that's why it's so complicated to actually estimate melt at a local level. So we have, for example, the location of a glacier, which matters a lot. It matters whether the glacier is, for example, in the tropics, or whether the glacier is in the Arctic. They have a very different climate. It matters which elevation the glacier has. So higher elevations usually have colder temperatures than lower elevations. It matters which slope angle the glacier has, because it matters for the dynamic flow of the glacier. It also matters which size the glacier has and which ice amount is actually available for melting. It matters whether the glacier is south-facing or north-facing, because it will matter for the direct solar radiation that can be absorbed by the glacier surface. It also matters how much dust there is actually on the glacier, or how much cryoconite, which is some organic matter that can be accumulated on a glacier, and also black carbon, actually. It also matters how many rocks there are on the glacier surface. It matters where we are, so basically whether the glacier is marine terminating or whether the glacier is land terminating. And last but not least, the human influences matter. So it matters whether we have some tourism facilities nearby, so for example, a skiing resort, or some other urban built environments, such as factories in the vicinity of glaciers. So all this is to say, local glacier modeling is complex, because we need to take all of these factors into account. So this is my study region in Western Canada. We have 20,000 glaciers here. And I've disaggregated this study region into 10 different subregions that are spanning from the east, from the Rocky Mountains, to the west, for the coastal mountains, and you can see Vancouver here at the bottom. And I would like to start with asking you, what do you think? How many of these 20,000 glaciers do actually have local mass balance observations? Who wants to have a guess? 2. Okay.
1,000.
1,000? 10? So actually it is 17. So out of the 20,000 glaciers, we only have 17 glaciers with mass balance observations, which actually shows you that there is a huge lack in observations that we can use to constrain our glaciers and to constrain our mass balance observations for our models. And if you have a closer look, actually, in the years where we do have mass balance observations, this is what it looks. So in gray, you can see all the years without any observations. And in red, you can see the years that do have net mass balance observations. That means that we know how much the glacier is melting in the summer and how much mass it is actually accumulating in the winter. So what we can see is those are very few years. So we don't have much information from local observations that we can actually use for our glacier modeling. So what do we do? I've contributed to new observations. So this is a photo from my fieldwork on Kaskawulch Glacier, which is a large glacier in the Yukon Territory in the north of Canada. It is around 60 kilometers long. And so what we've done is, besides of measuring how much the glacier is melting, we've also set up an automatic weather station. And we have actually measured which fluxes, or which physical fluxes are actually contributing to the glacier melt. So this could be temperature, this could be wind speed at different elevations. This could be the solar radiation and the long-wave radiation or the turbulent fluxes. And the reason why I mentioned Pascal-Wulch Glacier here is because I want to introduce my first example of local glacier impacts. Pascal-Wulch Glacier is a really important glacier because it is melting very rapidly. Here we can see photos from 1900 and 2012, where you can see the glacier tongue, so the terminus. It has been decreasing rapidly. And the reason why this is so important in this case is because there has been a devastating event in 2016, which is called river piracy. So before that, Pascal-Wulch Glacier was feeding Kluane Lake, which is a huge lake in the west of Canada. So basically, the meltwater from Pascal-Wulch Glacier was running northwards through Kluane Lake and then towards the Bering Sea. But because the glacier has retreated so much, the glacier meltwater has actually changed its course. And now it is flowing first eastwards and then southwards, right into the Pacific Ocean. So I will show you again. This was before 2016. And here, this is how it looks like after 2016. And Kluane Lake is a really important fishing ground, especially for indigenous communities, but also for other communities around. It is a really important winter transport route. It is a really important area for salmon spawning, and of course for freshwater supply. So all this is to say that this retreat from this glacier has direct impacts for this local community. Here you can see the drained lake, so the water level has actually decreased by several meters. So I've just mentioned we do have scarce measurement on glaciers. We don't have many observations that we can actually base our estimations off. So what do we do if we don't have direct measurements of local glacier changes? Well, one of the ways we can measure local glacier changes is through satellite imagery. So, for example, through digital elevation models. Another way is through aerial photography that we can use, or through radar. Then, of course, we can use data from weather stations to indirectly model the weather, and through that, basically the glacier melts. And last but not least, we can use indirect measurements from the stream flow, where we can actually see how much water the water levels have increased in these streams. So what I would like to focus on now is actually these indirect measurements for glacier melt that we can see through stream flow. And I would like to start us off with an example from the unprecedented Pacific Northwest heat wave in 2021. So this was a devastating event that lasted for several days, where the temperatures reached more than 50 degrees Celsius in one city in Canada. This was the first time that this temperature was reached above 45 degrees latitude north. It led to 1,400 deaths that can be directly attributed to the heat wave. And it led to massive wildfires and to the loss of billions of sea creatures. But one of the less known consequences, actually, of this heat wave is its influence on glaciers and on stream flow. So here I would like to show you the impacts that it had on stream flow. So in blue, you can see the 40-year average stream flow for a non-glaciated basin, so a basin that is not depending on glaciers. And in black, you can see the stream flow during this heat wave. And in red, I'm showing the time of the heat wave. So what you can see, during the heat wave, there's a strong stream flow response. And after the heat wave, there are very low flows. They're so low that they could not sustain a drinking water supply for this community. And second of all, I would like to show you the same stream flow response, but now for a highly glaciated basin. So what we can see is that during the heat wave, we can see an extremely strong response with very high stream flows that led to extreme flooding in that region. But after the heat wave, we can actually see completely normal flows. So what I want to highlight here really is that the glaciers are this balancing factor in our climate system. And that even after kind of this devastating event, such as this heat wave, glaciers can actually balance our drinking water supply and make sure that we do have all of this following these devastating events. However, if glaciers are melting, we will not have that balancing factor, which was led probably in stream flows being even more devastating in the future. So decreasing glacier mass leads to scarcity and especially unpredictability of freshwater supply in the summer. That is when water demand is at its highest. And to end, I really want to stress that it's important to decarbonize now and to have ambitious climate targets, because it does really matter how our glaciers behave, and not only at the global scales, but especially at local scales where communities can feel the impacts that are directly affected, like in the vicinity of glaciers, but also the millions of people that live further downstream. And with this, I would like to hand over to David, who will talk about local glacier impacts in other regions. Thank you.
Thanks, Christina. That was wonderful. So I'm going to now take a little bit more time. We addressed the global impact slightly, and now I'm going to take us sort of on a journey around the world to think about how these local impacts are experienced by really a variety of communities. And these are the things that include things like glacier outburst floods, water resources, the tourism, the cultural components, and also have a framework in mind as to how these are going to change depending on what we do with our greenhouse gas emissions. Try again. Abracadabra. Perfect. So as I mentioned, this is the glacial lake, or the glacier that I did my PhD on in Nepal, in Jasho. And in 2007, between 1955 and 2007, there we go, this glacial lake formed. And this glacial lake was thought to be a hazardous glacial lake. It was thought to be a risk for the downstream communities. And so a lot of resources went into thinking about how this hazard is going to evolve in time and how this hazard could be mitigated. How can we reduce the flood risk for downstream communities? And so what ended up happening was there was a United Nations Development Program project that invested a lot of money in order to reduce the level of this lake by 3 meters. And so now Imja Lake has been lowered substantially, but the glacial lake is still retreating further back, which puts it at a risk of having an avalanche or a rockfall land in the lake, generate a tsunami-like wave that can then still be a flood hazard to the downstream communities. The good thing is that by reducing this lake by 3 meters, there's now more of a buffer, there's more of a barrier that wave would have to overtop, and there's also less water volume that is present for the flood that is downstream. The other thing that's incredibly impressive about this is this glacial lake was located at 5,000 meters. This is incredibly high altitude, right? Helicopters had to deconstruct some of the heavy machinery to be able to put it into the helicopter, transport it to 5,000 meters, and then reconstruct the heavy machinery such that they could move all of the earth, do this excavation, and make this possible. So even though it only lowered the lake by 3 meters, it is an incredible symbol as to what is possible in these high altitude communities to reduce the risk associated with these glacier outburst floods. Now here's an example of Lake Palpacocha, which is located in Peru, the other side of the world, right? Here's what the lake looked like, a rendering of it in 1932. It had a volume of approximately 12 million cubic kilometers. In 1941, there was a glacier outburst flood. It killed approximately 1,600 people in the city below of Juarez. This really was a wake-up call for Peru in order to start managing the risks associated with their glacial lakes, right? Remember this time frame, 1941, they had already had this devastating glacier outburst flood. In Nepal, Imja Lake that we were talking about, it still looked perfectly fine in the 1950s, right? So we have different time scales at which these local communities need to think about these adaptation measures. One important thing to consider is that afterwards, this glacial lake, all of its water was drained, right? So the hazard is essentially zero, right? You no longer have to worry about this. Or do you? Now, 2013, we see that the glacial lake has come back. So now there are siphons that are located at Lake Papacocha that drain some of that water, try to get some freeboard in order to reduce the risk for downstream communities like Juarez to ensure that that does not happen again. Right? And so this is what it looks like in present day, where you start to see all of the surrounding topography, those avalanches that could fall into the lake, create a tsunami-like wave that creates that flood downstream. And you can look at the flood hazard assessment associated with this for different amounts of lowering the water level, right? So here's where the science as to how these glaciers are going to evolve, how these glacial lakes evolve, has to come into play with the modeling and the engineering design in order to design these climate resilient systems moving forward. Here's an example going now up the coast, all the way up to Alaska and North America, of Mendenhall Glacier. Mendenhall Glacier, you can see an image from about 1893, the early, right around 1900, and now present day. What you can really see here is that Mendenhall Glacier, as we've shown in many images already, has thinned. But I also want to turn your attention to Suicide Basin right here. It now is the location of an ice dam glacial lake that since 2011 has grown and become an outburst flood every single year. Last year and over the last 2 years, this has had the highest amounts of flooding downstream associated with this ice dam glacier outburst flood. So much so that it has started to impact the houses that you can see in Juneau and the surrounding community. Here's a glacier outburst flood that we observed when we went into the field during our PhD research. We were supposed to be looking at Imjasho. This was an outburst flood that happened from a glacier nearby. It was sourced not by a proglacial lake, but by glacier water that was stored within the glacier. And you can see right here on the right is that's actually a local lodge. That's the patio associated with a local lodge. So we went up to study Imjasho, and yet when we got there and we were coming down for a community meeting, we literally couldn't cross the bridge because an outburst flood was happening. And so we turned our attention from working on Imjasho to start to do a couple of days analyses to try to understand what was the source of this flood. And in talking with community, they shared that things like this had happened before. This wasn't the first time. It was just one of the first times that we had been present to see it. And we didn't really know about it from satellite imagery because most of the water was stored below the surface of the glacier. And so what this really shows, right, is not only how the floods evolved, and in this case, right, it's a smaller outburst flood, so the risk to the communities is lower, but also how important that local knowledge is, right? They had seen these outburst floods before. They know that these things like this exist, and so being able to incorporate that local knowledge is absolutely critical. And so here I want to show is a map as to how this type of outburst flood varies depending on where you are in the world. So you can see in Alaska, for example, it is predominantly white. The white circle means that most of the glacial lake outburst floods that we see in Alaska are coming from ice dam glacial lakes like I showed you in Juneau. When we start to look in Peru, for example, in the Andes, we start to see a lot more of that yellow-orangish color, right? More than 50% of these are formed by those moraine dam glacial lakes. What does that mean? It means that the processes that which we need to study are going to be very regionally specific. If you're looking at outburst flood hazards in Peru or in high mountain Asia, in the Himalayas, for example, you're likely going to be focusing on those moraine dam glacier outburst floods. If you're looking at the hazard in Alaska, or for example, Southwest Asia, here the Karakoram, for example, you're going to be looking a lot more at those ice dam glacial lake outburst floods. So we need to think about both of these when we start to think about the local scale at which we need to evaluate and plan for. And here's an example of moraine dam glacial lake outburst floods and how that risk is going to evolve or is estimated to evolve in the future. And this study, which came out a couple of years ago, showed that the glacial lake outburst flood risk from these moraine dam glacial lakes in high mountain Asia is expected to triple by 2100. This is in large part because we expect to see a lot more glacial lakes forming as these glaciers retreat in response to our actions and our greenhouse gas emissions. Shifting gears a little bit, right? That was focusing on glacier outburst floods. We also think about our glaciers. They are a very important water resource. Now, the glacier runoff is going to change over time. And so right now I want to think about the annual glacier runoff. If we start to melt our glaciers, which we are actively doing, our glaciers are a reservoir. And as you melt the glaciers, you're essentially opening up the reservoir. You're releasing water downstream. And so we see this peak in glacier runoff in the future. It's dependent on our emission scenario. If we have higher emission scenarios, this peak is going to be higher, right? If it is lower, this peak is going to be lower. But after a while, you've opened up your floodgate, you've opened up your reservoir, and there's no more water to provide downstream. You don't have that natural system, right? And so you start to see a reduction. That means we're going to have less water resources available, and we need to plan accordingly. That was at an annual time scale. If we think about seasonal time scales, we can think about traditionally the glacier melt shown here in green really kicks into play after the snow melt is gone, right? So in the summer, in the end of summer, when we hit that timing of peak water, we start to see we have a big increase in the glacier melt, especially in the summer and the end of summer. After those glaciers are gone, we start to see a massive reduction. And so the seasonal impacts of this glacier runoff is very, very important depending on the region where you're located. So if we think about that peak water for some of the major river basins in high mountain Asia, I'm going to highlight two. We can see in the Indus River, for example, we expect the peak water to occur after the mid-century. So between somewhere about 2050 and 2070, dependent on that emission scenario. Once again, higher emission scenarios, more glacier mass loss, more glacier melt, it's going to cause higher amounts of peak magnitude, and it's also going to delay it. If we look at other aspects of the other river basins, like the Brahmaputra, we estimate that it's already past that period of peak water. What does that mean? It means that glacier, the runoff from those glaciers in the Brahmaputra is going to have to come from somewhere else, right? Individuals, downstream communities, they come to depend on this glacier runoff, right? And what we find is that if that glacier runoff is not going to be present, then they might be needing to rely on things like unsustainable groundwater use, which is already stressed, right? So we have to factor in what these changes look like as we plan our climate resilient futures and our systems to respond accordingly. The other thing that I want to note is what I just showed you was estimates of glacier runoff. We know that the glacier runoff moves downstream and moves through our hydrological system. And that's incredibly important to us to think about its role within the entire water cycle. So some new models that we can do, we can couple our glacier models to hydrological models. And what's really exciting with this water balance model coming out of the University of New Hampshire is we can actually track where that glacier runoff goes downstream, how it is used, for example. So I'm going to show you that here for just an example. So it takes our model glacier runoff. It then looks at how that glacier runoff is flowing downstream in our major river basins. We typically do these analyses on a basin by basin level because that's where we think about managing our water resources. And here's an example of how much water is used for irrigation, right? So the glacier runoff, it might be a small fraction of what is used in irrigation, but again, it's an important contribution to that glacier irrigation. And it can be especially important at the end of summer in non-monsoonal systems, right? And this is not just high mountain Asia. So Chile, for example, especially here's a picture of the city of Santiago. They've been having a mega drought that's been going on since 2010. If we look at the amount of water before and after that mega drought, we can start to see how important that glacier runoff is, right? So the percentage of the glacier contribution is shown there, where it's approximately 30% before this mega drought. And now that Santiago is in a drought, we see that it kicks up to about 43%. So the glacier runoff can be especially important in buffering droughts. And this is not just for high mountain Asia, it is for communities all around the world. The other thing that we like to talk about, right, is the glaciers are beautiful, right? It is one of the real pleasures of being a glaciologist that we get to go to these glaciers and study them, right? They're also a massive tourist attraction. So here's Marjorie Glacier, which is located in Glacier Bay National Park in Alaska. It's one of the most visited glaciers because cruises often come up and see this tidewater glacier. You can start to see the calving of the ice into the water. When we think about our future projections of Marjorie Glacier, we find that around the year of about 2050, it's going to actually retreat out of the ocean and become a land terminating glacier. That attraction that draws so many people and so many cruise ships to come and experience the beauty, to raise that awareness of why these glaciers matter and how they're changing, is going to be changed. You're going to see a land terminating glacier. At the same time, it's really important to think about how much glacier mass can be preserved by 1.5 degrees if we reduce our greenhouse gas emissions rapidly versus 3 or 4 degrees. Where that glacier ends up is completely different. And that also is going to impact how much we can see that glacier from the ocean and from those cruise ships. We do this analysis for all the glaciers in various Alaskan national parks, for example, and we can see it's highly variable. Some national parks are going to essentially lose their glaciers. They're going to be completely deglaciated. Others, for example, Glacier Bay, Denali, some of the largest glaciarized regions in Alaska, they're going to have experiences of considerable glacier mass loss that is highly dependent on that emission scenario or that temperature change scenario. Once again, our actions here as a society can have a huge impact on preserving our glaciers. And it's not just Alaska. Here's the Lech Glacier, which is a World Heritage Site. It's one of the largest glaciers in Central Europe. And you can see how it looks like between 2020 and 2100 for a low emission scenario on the left and a high emission scenario on the right. We experience a lot of mass loss out through 2050 and beyond 2050, where the differences in emission scenarios really kicks in is when you start to see where we almost are completely deglaciating this massive glacier versus at least having some that we are preserving for future generations to appreciate. A study that came out about 4 or 5 years ago showed that the World Heritage Sites, the glaciers in these regions are expected to lose anywhere between about 30% and approximately 70% or 60% of their glacier mass. So once again, these World Heritage Sites where glaciers are located are literally all around the world. And they have already been designated as a vital resource, a vital cultural symbol, right, for our global community. Our actions can start to preserve that resource, can preserve them for future generations to be able to experience and to be able to appreciate. Khumbu Glacier, right next to where I did my PhD, is a major iconic trekking, right? Base camp for Everest on the Nepal side is located on Khumbu Glacier. Many people come up to try to summit the world's tallest mountain. They go through the Khumbu icefall. We can see that the glacier is going to retreat substantially. At Khumbu icefall, though, with 1.5 degrees, we project that ice will still flow through it all the way down to roughly Everest Base Camp. For those higher temperature change scenarios, we're estimating that ice is actually going to go above the Khumbu icefall. So this iconic trekking route, right, is going to be fundamentally changed. How that changes the hazard, how the rock falls, the avalanches and surrounding terrain changes is going to be very important moving forward as well. But here you can show our actions as a society have a huge impact on what these glaciers are going to look like. The last one that I want to show is Kaweroi Mato Hinehukatere, which is located in New Zealand. That's its Maori name. And there is a beautiful oral tradition associated with this glacier. Hinehukatere, she took her lover, Tuave, up into the mountains. Tuave was unable to keep up with her, and Tuave ended up falling and being swept away by an avalanche. And Hinehukatere, she cried and she cried and she cried so much that the gods perpetually froze her tears as a memorial moving forward. And that is what the glaciers are. It's the tears of the ice avalanche maiden. And so, as one Maori individual noted very well, and I think could not be stated better, it's more than just a physical loss. It's a spiritual depletion, a depletion of our ancestral heritage and the devaluation of our past. These are not just glaciers and water resources that we use as a society they are also incredible cultural symbols that are passed down for indigenous communities around the world. And here is what Karoi Mato Hinehokateri looks like in the future. We start to see New Zealand is incredibly sensitive to what our greenhouse gas emissions look like into this temperature change scenario. You're looking at losing approximately 30% of the mass versus losing close to 90% of its mass in a +4 degree scenario. Once again, our actions have a huge impact. So what I want to leave you with is the fact that our glaciers, they tell us stories. They literally are a part of oral traditions for many communities around the world. They also tell us the story of climate change that we can see so apparently, that can draw us to action, right? The key thing is that we have the ability to write their future stories. And the reality is that if we want to make it a positive one, we must limit our temperature increase to 1.5 degrees, and every increase in temperature matters. Thank you very much. Happy to take questions with Christina as well, if anybody has them.
Consultants, with a question. I'm coming from Munich in Germany. I'm talking to representatives of companies in Germany and also governments. And I have to explain them which RCP scenario would have what kind of effect. So everybody in my audience is expecting that they could use the less bad scenario. When I use the scenario of 8.5 degree in order to realistically predict what is going to actually happen in the next 20 years.
That's a great question. So I think just saying, for those who couldn't hear it, it's sort of asking what should be the scenario that you use and how should you be conveying that information to the policymakers that are going to make decisions around infrastructure in this case, right? What I can just say is that you need to plan for the risk that you're willing to take, right? We are present here having a direct impact as to which emission scenario we can go on, right? What are the climate pledges going to look like? And whether it's in Germany or whether it's any island nation or any high mountain community, right? That is a decision that these delegates can bring together, right? From a planning perspective, you can think about planning for a worst case scenario, planning for a best case scenario, or some adaptive strategy where you plan for the best case scenario, but you have flexibility in your adaptation strategies where if things are moving towards those higher emission scenarios, you can plan your systems accordingly. I think that's going to be one of the ways that we have to move forward, especially given all of the uncertainty that we have and what's going to happen. It's a great question. Any other questions? Well, I'll stick around. I'd be happy to talk to people and really appreciate you coming here and listening. Thank you so much.